In this video, we're going to talk about trigonometry as it's related to right triangles. Let's just remind ourselves of what sine and cosine were, or at least how they're defined. We define the sine and cosine functions using the unit circle, which is the circle with equation x squared plus y squared equals 1. That's the circle with center at the origin, 0, 0, and having radius equal to 1. If a central angle having radian measure theta is drawn in the unit circle in standard position so that the initial side is along the positive x-axis, then the point where the terminal side of the angle intersects the unit circle has coordinates x equals cosine of theta and y equals sine of theta. Again, this circle is the unit circle, so the radius has length 1. Theta is the angle measure. If theta is positive, it corresponds to a counterclockwise rotation. If theta is negative, it corresponds to a clockwise rotation. We want to relate this to right triangles. The coordinates of the point cosine theta, sine theta give the height and base of a right triangle having radius 1 and angle theta. So the coordinates of this point right here are x equals cosine of theta and y equals sine of theta. Cosine of theta, that's the x-coordinate, so that gives us our horizontal distance away from the x-axis, or away from the y-axis, so that's x. Sine of theta, that's our y-coordinate. That tells us our vertical distance away from the x-axis, so that tells us how high our triangle is. That's y. So here we have a right triangle where the base has length x, which is cosine theta, and the height of this triangle is y, which is sine of theta. And this is a right triangle. It's a right triangle where the hypotenuse is length 1 because that's the radius of the circle. And this angle is the central angle, which has measure theta. So we can see that given a theta, we can construct a right triangle so that the sides of that right triangle are cosine theta and sine theta. If a circle with center at 0, 0 has radius r, which is not necessarily 1, then the central angle of measure theta, in terms of radians, in standard position, will intersect the circle at the point with coordinates r times cosine theta and r times sine of theta. So now we've just either stretched the circle or made it a little smaller. And when you do that, you make the radius bigger or smaller. And when that happens, the coordinates are either stretched or compressed. So the x-coordinate, again, this tells us how far away we are from the y-axis. This gives us our horizontal distance. So this is r cosine theta. That's the base of this right triangle. The height of this right triangle is given by the y-coordinate, which is r sine of theta. That's this distance here. So this is r times sine of theta. It's the y value, the y-coordinate. Consequently, a right triangle with base angle theta, referring to this angle here, and hypotenuse having length r, which is this length here, so let's just label that r, has a base length of x, which is r cosine theta. So that's this length right here. This is r cosine theta. This is a right triangle, so maybe I'll put that little indication there. The altitude, or the height of this right triangle, is given by the y-coordinate, so that's r sine of theta. So that's this length right here. So it's r times sine of theta, like so. So what does that tell us? Well, let's look at this one, r cosine of theta. That's equal to x, as we see here. If we divide both sides of this by x, or not by x, if we divide both sides of this by r, then these two r's will cancel. and you'll just have that x over r is cosine of theta. So cosine of theta is x over r. We can do the same sort of thing with sine. If we divide everything by r, then these r's will cancel, and now we have y over r is sine of theta. That's what we have here. Y over r is sine of theta. What this does for us is this allows us to relate sine and cosine of an angle to measurements of the right triangle. So remember what r is. R is the length of the hypotenuse of this right triangle. We're looking at this right triangle here. This right triangle. And we can see that cosine of theta is equal to x over r. R is the length of the hypotenuse. And what about x? X is the length of the base. So that's this length right here. So this length, which we're calling r cosine of theta, that's x. So this cosine of theta is equal to x over r, and that's equal to the length of the base divided by the length of the hypotenuse. And we have something similar for sine of theta. Sine of theta is y over r. R again is the length of the hypotenuse, but what about y? Y is the vertical distance above the x-axis. That's this length right here. That's y. So sine of theta is y over r, but that's the height of the triangle, or the altitude. So we'll write that as the length of the altitude divided by the length of the hypotenuse. What about tangent? Tangent is sine over cosine. So tangent of theta is sine of theta over cosine of theta. But sine is y over r, and cosine is x over r. Dividing by a fraction is the same as multiplying by the reciprocal, so this is y over r times r over x. The r's cancel, and you're left with y over x. Y over x, which you see here. So y is the length of the altitude, which I'll just call alt period, and x is the length of the base. So you can see that cosine, sine, and tangent can all be expressed in terms of dimensions of this right triangle. Let's introduce some terminology that we'll use just to make it a little bit easier. So suppose that we have a right triangle, and we have an angle, an acute angle that we're calling theta. So we can name the sides of the triangle relative to that angle theta, as in the figure you see here. So the side next to the angle theta is called the adjacent side. The side opposite the angle theta is called the opposite side. And of course we'll call the hypotenuse. Usually we'll even abbreviate these. So the adjacent side we'll just write ADJ, opposite side we'll write OPP, and hypotenuse we'll just write HYP, like so, just to make it a little bit easier to write it down. Any right triangle can be placed in a circle so that the non-right angle theta is a central angle in standard position, and the radius of the circle is the length of the hypotenuse. So you can think about this in terms of a construction by placing the center of the circle at the angle theta and just drawing a circle having radius r, where r is the length of the hypotenuse. This can always be done for any right triangle. So in this case, r will be the length of the hypotenuse, and x will be the length of the adjacent side, and y will be the length of the opposite side, like so. So now we suppose that we have a right triangle with acute angle measure theta, this one here. In that case, the cosine, sine, and tangent functions can all be computed using the formulas that you see here. So cosine theta is the adjacent side over the hypotenuse, and I mean the length of the adjacent side divided by the length of the hypotenuse. This just comes from the previous slide. So if we go back, we can see that in order to compute cosine of theta and sine of theta, we just have to use these dimensions of this triangle. So remember that we saw that if you had a circle of radius r and a central angle measuring theta, then these coordinates x comma y were r times cosine of theta comma r times sine of theta. So x, which is the length of the adjacent side, is r cosine of theta, and that was equal to x. And the opposite side, that's equal to y, which is r sine of theta, so that's equal to y. So remember, we can solve for cosine of theta by dividing by r, x over r. So this is going to be x, which is the length of the adjacent side, divided by r, which is the length of the hypotenuse. And similarly, sine of theta is y over r, but y is the length of the opposite side, divided by r, which is the hypotenuse. So that gives us these formulas. Cosine of theta is the adjacent over the hypotenuse, the length of the adjacent side over the length of the hypotenuse, and sine of theta is the length of the, that should just be OPP. Sine of theta is the length of the opposite side divided by the length of the hypotenuse. Tangent is sine over cosine. So if you look at sine over cosine, that's going to give you the opposite over the adjacent. Again, if we look on the previous slide, we will see that tangent is sine over cosine, and we know that tangent is equal to y over x, which is the length of the opposite side over the adjacent side. So that's why we get that tangent is opposite over adjacent. So that gives us these handy formulas for computing sine of theta, cosine of theta, and tangent of theta using a right triangle. Alright, let's look at an example. For the triangle drawn below, compute cosine of alpha, sine of alpha, and tangent of alpha, where alpha is this angle. So we can just use those formulas. We have a right triangle here, and we have the dimensions of all of those sides, and that's what we need. So cosine of alpha is the adjacent side, the length of the adjacent side, over the length of the hypotenuse. Well, the adjacent side is length 5, and the hypotenuse is the side opposite the right angle, so that's 13. So cosine of alpha is 5 over 13. What about sine? Sine of alpha is the length of the opposite side over the length of the hypotenuse. Well, the opposite side is length 12, and the hypotenuse is length 13. So that's our answer for sine of alpha. Tangent of alpha is opposite over adjacent. So the opposite side is 12, and the adjacent side is 5. So it's 12 over 5. So those are the values of cosine alpha, sine of alpha, and tangent of alpha. Let's do another example. In this example, we're given the length of one side, which is length 8, and we're given the measure of one angle, which is 30 degrees. 30 degrees is pi over 6 radians. So given this information, we want to figure out the length of the base of this triangle and the length of the hypotenuse. So let's label them. Let's call this one B and C. And our goal is to determine the values, so find the values of B and C, given what we know here. So what do we know? Well, we know that this angle is 30 degrees or pi over 6 radians, and we know that this opposite side is equal to 8. So we know the opposite side, and we want to find this hypotenuse. So the trigonometric function that relates the opposite side and the hypotenuse is the sine function. So sine of pi over 6 is going to be equal to the opposite side over the hypotenuse. The opposite side has length 8. The hypotenuse, which is something we're trying to learn, has length c. We don't know what it is yet. What we do know is we do know the value of sine of pi over 6. If you can't remember, it might help to draw a quick little unit circle here. So pi over 6 is roughly that angle. It's the one where the x value is larger than the y value. So the x value is square root of 3 over 2, and the y value is 1/2. And 1/2, the y value, that's sine of pi over 6. So this angle is pi over 6. So that tells us that this length is 1/2. So we have that 1/2 is equal to 8 over c. Or in other words, if we cross multiply, c is equal to 2 times 8, which is 16. So c is equal to 16. Okay, so that tells us c. We still need to figure out the value of b. And for that, we're going to use a different trigonometric function. For that one, we're going to use cosine. So cosine of pi over 6 is equal to the adjacent side, or the length of the adjacent side, over the length of the hypotenuse. The adjacent side, that's the thing we're trying to figure out, b. But the hypotenuse we know, that's 16. We also know the value of cosine of pi over 6. That's the x value right here. Cosine of pi over 6. So the x value is square root of 3 over 2, and that's cosine of pi over 6. So that's square root of 3 over 2. So that means we know that the square root of 3 over 2 is equal to b times 16. So we solve for b by multiplying both sides by 16, and we'll have that b is equal to the square root of 3 over 2 times 16, which is 8 times the square root of 3. And that's our value b, 8 square roots of 3. So that means we know what c is 16, and we know what b is. B is 8 square roots of 3, and that's what we wanted to find. Let's do another example. For the triangle drawn below, determine the lengths of the unknown sides. In this case, the unknown sides are the opposite adjacent sides. We're given an angle here which is 65 degrees. We're also given the length of the hypotenuse. So what we want to do is we want to find the lengths of the other two sides. So we'll call this one A, and we'll call this one B, and our goal is to find A and B. Find the values of A and B. That's our goal. So how are we going to do this? Well, we're going to use trig functions again. So for example, we know that cosine of 65 degrees is equal to the adjacent side over the hypotenuse. Well, the adjacent side is A, and the hypotenuse is 18. So that tells us that A is equal to 18 times cosine of 65 degrees. Well, what's 65 degrees? It might help if we know what 65 degrees is in terms of radians. So 65 degrees is 65 degrees times pi over 180 degrees. And this gives us 13 pi over 36. In that case, we know that A is equal to 18 times cosine of 13 pi over 36. Now, this is a value that we're not likely to be able to compute on our own. But if we use a calculator, this is approximately 0.422618. And so if we do 18 times that, that's going to give us that A is approximately 18 times 0.422618, which gives us approximately 7.60713. So that's the length of A, approximately. In order to get B, we're going to use sine. So sine of 65 degrees is equal to the opposite over the hypotenuse. The opposite side, we don't know the length of that. We're calling that B. That's what we're trying to find. The hypotenuse we do know is length 18. So just multiply 18 over to the other side, and we're going to get that B is equal to 18 times sine of 65 degrees. And again, 65 degrees is 13 pi over 36. So B is equal to 18 times sine of 13 pi over 36. And we're probably going to need a computer or a calculator for this as well. This is approximately 0.906308. So B is approximately the product of 18 with 0.906308. So that's going to give us that B is approximately 16.3135. And that's the value of B, at least approximately. For our next example, again we have a triangle, but this time we want to determine the length of the base if the altitude is known to be 10. So note that this is not a right triangle. This angle is 60 degrees and this angle is 25, so that means that this angle here is 95 degrees rather than 90, so this is not a right triangle. What we do know is that the altitude has length 10, and we want to determine the length of the base, so that's this whole length. Now, if we don't have a right triangle, you might wonder how are we going to use right triangle trigonometry. Well, notice that this altitude divides the big triangle into two smaller triangles, and each one of those is a right triangle. So for example, here we have a right triangle where one of the angles is 60, the other angle is 90, so we have here a 30-60 degree right triangle. On the other side, this triangle is also a right triangle, where here we have a 90-degree angle, a right angle. This is a 25-degree angle, and so that means that this is a 65-degree angle here. So we're going to use these smaller right triangles to answer this question. So what we're going to do is we're going to call this length A and this length B. And then the length of the base, our goal, is to compute A plus B. That's what we're looking for. We want to figure out the value of A plus B. So if we figure out the value of A and then figure out the value of B, that will give us the answer we seek. Alright, so how are we going to go about doing this? Well, the first thing we'll do is we'll solve for A. So here we have a triangle, a right triangle, and we want to determine the length of the base given the length of this altitude. So in terms of this angle 60 degrees, we want to find the length of the adjacent side, and we know the length of the opposite side. So we want the length of the adjacent, we know the length of the opposite. So the trigonometric function that links the adjacent side to the opposite side is the tangent function. So tangent of 60 degrees is equal to opposite over adjacent, which in this case is 10 over A. Now 60 degrees is pi over 3. So tangent of pi over 3 is equal to 10 over A. We want to solve this for A. So we can multiply the A over to the other side. A times tangent pi over 3 is equal to 10. And then we divide by this tangent term. So A is equal to 10 over the tangent of pi over 3. And if we use a calculator or a computer, we get that this is approximately equal to 5.7735. In fact, we actually know what tangent of pi over 3 is. This is actually equal to the square root of 3. But we're just going to compute this using a computer because we want to know what the approximate value is when we sum it up. Okay, so that gives us the approximate value of A. The next thing to do is to find the approximate value of B. And we're going to do it in basically the same way, but now we're going to use this angle 25 degrees. So 25 degrees, if we convert that into radians, that's 25 times pi over 180, which is equal to 5 pi over 36. So that tells us if we do tangent of this 25 degree angle, which is 5 pi over 6, or excuse me, 5 pi over 36, that's going to again be equal to the opposite over the adjacent. But now we're looking at this angle here. So the opposite side is 10, and the adjacent side is b. So again, we want to solve for the denominator there. We want to solve for b. So we can multiply it over to the other side, and we get that b times tangent of 5 pi over 6, or 5 pi over 36, is equal to 10. And then divide by this tangent term. If we do that, we get that b is equal to 10 divided by this tangent. So it's tangent of 5 pi over 36. And now this one I can't do in my head, but I can use a calculator or a computer, and I find that this is approximately 21.4451. So that gives us the value of A and the value of B, but what we're interested in is A plus B. So A plus B is approximately the sum of these two. So 5.7735 plus 21.4451, and if you add these two together, you get that A plus B is approximately 27.2186. And that's your answer. That's the approximate value of the base. All right, let's do another example. A tree casts a shadow that measures 30 feet in length. The angle the shadow makes with the ground is 20 degrees. So how tall is the tree? So basically the idea is we have the ground here, and then there's some tree right here. And let's make that look kind of like a tree. And the shadow that this casts, well, it meets the ground at an angle of 20 degrees for this angle here. The length of the shadow, we're told, is 30 feet. So our goal is to figure out what the height of the tree is. Let's call it h. So we want to find out what h is. We want to figure out what h is. So again, we know the adjacent side, adjacent to this angle, and we want to know what the opposite side is. So we use tangent. So tangent of 20 degrees is equal to the opposite over the adjacent. Once again, we need to convert from degrees into radians. So 20 degrees is 20 times pi over 180, which is the same as pi over 9. So tangent of pi over 9 is equal to h divided by 30. So again, we want to solve for the unknown. In this case, it's in the numerator. So we just multiply both sides by 30, and we get that h is equal to 30 times tangent of pi over 9. And this is approximately equal to 10.9191. So in other words, how high is the tree? Well, it's just under 11 feet. This brings us to another definition. Two angles are said to be complementary if their measures add to 90 degrees, or pi over 2 radians. In a right triangle, the two acute angles are complementary angles. They necessarily add to 90 degrees, or pi over 2 radians. So in this triangle that you see here, we have a right triangle, so this is 90 degrees, or pi over 2, and then alpha plus beta must necessarily add up to the other 90 degrees. So for any trigonometric function, we have something called a cofunction. For example, if you have sine, the cofunction is cosine. The way that you evaluate the cofunction at an angle is by evaluating the original function at the complementary angle. So, for example, since cosine is the cofunction of sine, if you want to compute cosine of alpha, that's the same as sine of the complementary angle beta. Indeed, this is where the name cosine comes from. Cosine of an angle is the sine of the complementary angle. It's easy enough to verify this just by using the definitions. Here we have a triangle where the two acute angles are alpha and beta, and we want to show that cosine of alpha is sine of beta. Cosine of alpha, we know, is equal to the adjacent side over the hypotenuse. Well, let's give some names to the sides of this triangle. So let's call them A, B, and C. With these labels, the adjacent side, at least adjacent to the angle alpha, is A. So this is A over the hypotenuse, which is C. What about sine of beta? Sine of beta is the opposite over the hypotenuse. But now we're looking at the angle beta, and the opposite of beta is the side A. So it's A over the hypotenuse, which is C. So you can see that both of these are equal to A over C. So that tells us that cosine of alpha is equal to sine of beta. This leads us to what we call the cofunction identities. If alpha and beta are the two acute angles in a right triangle, then alpha plus beta is pi over 2, which is 90 degrees. Consequently, for an angle alpha in a right triangle, the complementary angle has measure beta equals pi over 2 minus alpha. And so we have the following cofunction identities. For any angle alpha, the following identities are true. Cosine of alpha is sine of pi over 2 minus alpha. So cosine of alpha is sine of the complementary angle. Cotangent of alpha is tangent of the complementary angle. Cosecant of alpha is secant of the complementary angle. We also have the other versions of these because in the same way that cosine is the cofunction of sine, sine is the cofunction of cosine. So sine of alpha is cosine of the complementary angle. Tangent of alpha is cotangent of the complementary angle. And secant of alpha is cosecant of the complementary angle. Let's just look at a quick example. According to the cofunction identities, cosine of pi over 3 is equal to sine of the complementary angle. Well, what's the complementary angle for pi over 3? It's pi over 2 minus pi over 3, which is pi over 6. Pi over 3 is 60 degrees. Pi over 6 is 30 degrees. So 60 plus 30 degrees gives us 90 degrees. So these are complementary angles. So cosine of pi over 3 is equal to sine of pi over 6. Now we know that this is true because we can compute these values exactly. Cosine of pi over 3 is 1/2, and sine of pi over 6 is also 1/2. If you're not sure about these, just sketch out a unit circle. So here's a unit circle. Let's just quickly draw in some axes here. So pi over 3 is roughly that, pi over 3. So this one has coordinates 1/2, comma, the square root of 3 over 2. So cosine of pi over 3 is the x-coordinate, which is 1/2. What about pi over 6? Well, let's draw another unit circle here. So pi over 6 is more narrow. This is pi over 6. You're dividing by a larger number to get pi over 6. So that means you get something that's a smaller angle. You're dividing by 6 instead of 3, so it's going to be a smaller angle. This one has x-coordinate, which is larger. So it's square root of 3 over 2, comma 1/2. And sine is the y-coordinate. Sine of pi over 6 is the y-coordinate, which is 1/2. So we can see that, yes, these two values are the same.